When two atoms are infinitely far apart, there is no interaction between them and the total potential energy of the system is taken as zero. As the atoms start approaching each other, electrostatic attraction acts between the positively charged nucleus of one atom and the negatively charged electrons of the other atom. According to Coulomb's law, the electrostatic potential energy between charges varies inversely with distance and can be written as U R equals minus ke squared R. As the separation R decreases, the magnitude of this negative potential energy increases, so the total potential energy of the system decreases. This decrease in potential energy means the system becomes more stable as atoms come closer. At a particular distance between atoms, called the equilibrium separation or bond length, the potential energy reaches a minimum value. Mathematically, this condition of stability is given by du doctor equals 0. At this point, the attractive and repulsive forces balance each other. The force between atoms is related to potential energy by F equals minus du doctor, so at the equilibrium separation, the net force is 0. If atoms are pushed closer than this distance, strong repulsive forces arise mainly due to nucleus-nucleus repulsion and the Pauli exclusion principle, causing the potential energy to increase sharply. This rise in energy shows that the system becomes unstable when atoms are too close. In solids, a very large number of atoms are arranged in a regular repeating pattern known as a crystalline structure. Because of this periodic arrangement, electrons experience a periodic potential inside the solid. According to quantum mechanics, electrons in such a periodic potential can only have certain allowed energies. These allowed energies form energy bands, separated by forbidden regions called energy gaps. The existence of these energy bands explains the electrical properties of solids. In conductors, the valence band and conduction band overlap, or the conduction band is partially filled. Because of this, electrons can move freely even with a very small applied electric field. The electrical conductivity of a material is given by sigma equals Ne mu, where N is the number of free charge carriers, E is the electronic charge, and mu is the mobility of charge carriers. In metals, the value of N is very large, so conductivity is high. In insulators, the energy gap between the valence band and the conduction band is very large, typically greater than 3 electron volts. Due to this large gap, electrons cannot easily gain enough energy to reach the conduction band. As a result, the number of free charge carriers N is extremely small, making conductivity almost zero. Semiconductors have an energy gap smaller than that of insulators, usually around 1 electron volt. At room temperature, some electrons gain thermal energy and jump from the valence band to the conduction band, creating free electrons and holes. The number of charge carriers in a semiconductor depends strongly on temperature and is given approximately by N proportional E caret minus Eg 2 kT, where Eg is the energy gap, K is Boltzmann's constant, and T is absolute temperature. This mathematical relation explains why the conductivity of semiconductors increases with temperature. Unlike metals, superconductors are materials that show zero electrical resistance below a certain critical temperature. Since resistance is given by R equals rho L, A, where rho is resistivity, L is length, and A is cross-sectional area, zero resistance implies that resistivity becomes zero in the superconducting state. In this state, electrons form bound pairs and move through the lattice without energy loss. Quantum mechanics plays a key role in explaining atomic and solid-state behavior. For the hydrogen atom in its ground state, the most probable distance of the electron from the nucleus is given by the Bohr radius A0 equals 4 pi epsilon 0. h squared me squared. The electron is described by a wave function, which gives the probability of finding the electron at a certain distance from the nucleus rather than a fixed orbit. This quantum mechanical description explains bond formation, molecular stability, and the electrical behavior of solids by linking microscopic atomic properties to macroscopic material characteristics.